Welcome to this video that's going to discuss topic 10b, the halogenoalkanes. This is the second part of the Unit 2 Organic Chemistry section. Part A is just the general principles, so I haven't made a video on that. It's literally just 2 pages, just going through all of the different terminology that we need to know. For example, oxidation, reduction, elimination, substitution. This is something that's fairly simple for you to be able to do yourself. What we're going to focus on today is the halogenoalkanes, and we're going to look at a number of different learning outcomes, and we're going to look at some past papers towards the end. So we need to be able to go over the nomenclature, and we need to be able to draw the structures of our halogenoalkanes. We have to be able to classify the different halogenoalkanes, looking at their reactions and some mechanisms, as well as looking at the relative rates of hydrolysis of our primary, secondary and tertiary, or our chloro, bromo or iodoalkanes. There are 2 core practicals within this topic, core practical 5 and core practical 6. I will not cover these in this particular video. You can find more information on those core practicals in the core practical video that will be uploaded into the IAS chemistry playlist. So please find there what you need in order to understand those practicals. So we're going to start off by looking at the halogenoalkanes. These are a homologous series of compounds, and they have the general formula CnH2n plus 1x. Now, of course, we do not classify these as hydrocarbons because they do have this halogen here, and the halogen could be a fluoro, a chloro, a bromo, or iodo. We tend just to focus on these 3, the chloro, bromo, or iodo. Sometimes fluoro can be there, and we very, very rarely talk about astatine. We also sometimes can simplify the formula of a halogenoalkane to just simply Rx. R meaning an alkyl group, so for example, methyl or ethyl. And the X is our halogen atom, so our fluorine, our chlorine, bromine, or iodine. When we are naming these halogenoalkanes, we name them very similar to our branched alkanes and alkenes. If we have more than one halogen atom, then they're listed alphabetically. So for example, if we take this center molecule here, we've got a carbon with 2 hydrogens and a bromine, connected to a carbon with 2 hydrogens, connected to a carbon with 2 hydrogens, and a chlorine. So with B coming before C in the alphabet, this becomes carbon number 1, this then becomes carbon number 2, and this becomes carbon number 3. And our halogenoalkane ends up being called 1-bromo-3-chloropropane. We can also have some other examples, as you can see in the table. I'll let you try and draw them and name them yourself. So the second thing that we have to be able to do with the halogenoalkane is we have to be able to classify them. Now, you have seen the terms primary, secondary and tertiary classifications before when you were discussing carbocations back in topic 5. We will also discuss primary, secondary and tertiary classifications when we do alcohols, and that will be in another video. So what do we mean by primary, secondary and tertiary? Well, it's all to do with how many alkyl groups they have attached, or you can look at it as how many hydrogens they have attached. So if we take, for example, this first one, if we look at just the end portion of our molecule here, so we have a carbon connected to 2 hydrogens and the bromine, which is connected to an R group. Because we only have one R group, we're going to call this a primary halogenoalkane. When we look at the second one here, I have a carbon connected to the bromine, and it is connected to 2 R groups and 1 hydrogen. So we call this a secondary halogenoalkane because it's connected to those 2 alkyl groups. Whereas the third one, you can see, is connected into 3 alkyl groups, and we call this a tertiary halogenoalkane. It's very important that we can distinguish between these 3 things because they can, depending on the classification, can depend on what sort of reactions we're going to get. So we need to understand why halogenoalkanes are reactive. if we consider hydrocarbons, hydrocarbons have only carbon and hydrogen atoms, and they contain very similar electronegativities, 2.5 and 2.2. Because they have such similar electronegativities, their bonds are almost non-polar. That means that the electrons are very nicely shared. We don't get any overall dipoles, so it's not particularly reactive to other molecules such as positive or negative ions or dipoles, or even lone pairs. This is why we require things like UV light in order for a substitution of an alkane to happen. When we compare this to the halogenoalkanes, they have a much larger difference in electronegativity in their carbon to halogen bond. We already know that the halogens are the most electronegative atoms in the entire periodic table. So because of this, we get polar bonds. Now, how does that have an effect? Well, it basically causes the carbon to have its electrons pulled away from it, and they will sit a little bit closer to the bromine, similar to the diagram here. And that causes the bromine to be a delta negative, and it causes the carbon to be delta positive. Now, the same thing will happen with fluorine, chlorine, or iodine. They will just have different levels of dipole activity, so one may be more slightly negative or slightly positive than the other, and we'll come back to that later on. So if this happens, it causes this carbon in the centre to become electron deficient. So that actually means that it attracts a nucleophile, and the nucleophile is something that is attracted to an area of low electron density. Because they're going to attract nucleophiles, they can undergo nucleophilic substitution reactions. And we're going to look at a couple of them later on in this video. The first reaction that we're going to look at is called a hydrolysis reaction. Now, hydrolysis, as you can see from the bottom bullet point, it can be split into two words. The hydro, meaning water, and the lysis, meaning to split. So this is basically the splitting up of a molecule using water. How this works is we have a delta negative oxygen on the water, because of course they have lone pairs, and these are going to be attracted to our slightly positive carbon of the halogenoalkane, and we make an alcohol and a hydrogen halide. Now we can write this hydrogen halide out in two ways. We can either write it as just HX, or we can write it as the ions that are present, H positive and X positive. That really doesn't make a difference, because our main focus actually is this part here, the alcohol. This is a way to make an alcohol from a hydrogen halide, from a halogenoalkane. By the end of this organic topic, you should be able to build a map that will show you all of the different organic reactions, but we'll come back to that a little bit later. Now, the hydrolysis reaction is actually very, very useful to us, because what it can actually do is it can help us determine the relative reactivity of these halogenoalkanes. And the way that we do this is we compare either a chloro, a bromo, or an iodoalkane, or we look at a primary, a secondary, or a tertiary structure. And these will tend to be bromoalkanes, but it doesn't matter. You can use chloro or iodo if you wish. This is a core practical. This is core practical 5. Now, I'm not going to go into the details of how we carry out core practical 5. You will find that information in a different video on the IAS chemistry playlist. Please feel free to check that out if you need it. We're going to look at what information this actually tells us. Now, the biggest problem with this particular reaction is that the products that are formed when we add in water are both colourless liquids. So we can't actually see when the reaction is finished without having to do a test, and we can't time that. So we need to be able to overcome this, because in order to time the reaction and get a rate, we need to physically see a change happening, whether that be a colour change or a mass change or something, or effervescence. Now, what we're going to focus on and what we're going to use to our advantage is we're going to use colour change. And we're going to achieve this using silver nitrate. Now, you've seen silver nitrate before back in GCSE, and it was one of our chemical tests. Now, I'm hoping that you can remember what the chemical test was, but if you can't, I'm going to help you out. And the silver nitrate, when it comes into contact with a halide, it's going to form a silver halide precipitate. And of course, we get different colours of the precipitate, so we can tell them apart as well. The only thing that we do need to be aware of here is that we have to dissolve the silver nitrate in ethanol. And that just helps us get over any miscibility issues, because our halogenoalkane and our aqueous solution are not going to mix particularly well, because we have an overall non-polar and polar substance trying to mix together, and we already know that like dissolves like. So there's going to be a bit of a problem there. So if we dissolve it into the ethanol, it's just going to be a little bit easier for us. So the first reaction that we're going to look at is we're going to be comparing our iodo, our bromo, and our chlorobutane. And it does not matter which alkyl group that you use. The IAS Chemistry Core Practical advises you to use butane compounds, but it does not really matter. Most likely they use butane because these are obviously all going to be liquids, and they are quite small molecules, so we don't get too many interacting intermolecular forces. So what we see from this is that we get iodobutane as the fastest, followed by bromobutane, followed by chlorobutane. Now, one of our objectives of this topic is to be able to understand the reasons why. It's very simple for us just to remember the order, but that would be something like GCSE. At A level, it is all about the why. And the why is actually a very, very simple answer, and it is all to do with the bond enthalpy. If we look at the difference in the bond enthalpy between carbon and iodine, carbon and bromine, and carbon and chlorine, we can see that the carbon and iodine has the smallest bond enthalpy. This means that it is the weakest bond. The weakest bond is going to be the one that is broken the most easily. When the weakest bond breaks, in this case our carbon iodine, we're going to form iodide ions. These iodide ions will very quickly mix in with our silver, and we will form a silver iodide precipitate. That's going to happen very quickly. When we get the bromine, it will continue to happen, of course, and we will make this silver bromide, and we will also make silver chloride, but the silver chloride is the strongest bond. Therefore, it takes the most amount of energy and therefore the most amount of time. So we can use bond enthalpies to explain why the iodobutane is the fastest. Okay, the carbon-fluorine bond is so strong that it is very, very rarely used in these hydrolysis experiments, because you can be timing for quite some time and still not see any precipitate being formed. When we test the different structural isomers, the pattern is that tertiary is the quickest, followed by secondary, followed by primary. Now, the good thing for AS level students is that you do not need to understand the reasons behind this trend, because it actually requires very much a deeper understanding of the reaction mechanism, and this is something that is going to be discussed in topic 11. It comes down to the fact that the tertiary and the primary undergo two different mechanisms that will have an effect on their rate. But we will discuss that when we get into year 13. So we need to know 4 key reactions of the halogenoalkanes, and you have to be able to draw the mechanisms for reactions number 2 and number 4. So that's number 2 and number 4. Now, I'm not going to go into any more detail about reaction number 1, because this is simply the hydrolysis reaction that we have just been looking at. So we're going to jump straight to reaction number 2, and this is known as a nucleophilic substitution reaction. And this just means that we're getting a substitution of an atom or a group of atoms, and it undergoes via a nucleophile. Okay, so reaction number 2 is to heat the halogenoalkane with aqueous potassium hydroxide under reflux, and this is another way that we can make an alcohol. Now, our attacking nucleophile in this case is the OH, and an example here is our chloropropane, 1-chloropropane being forming propan 1-ol plus our chloride ion. The mechanism for this particular reaction begins with the donation of a lone pair of electrons from this OH to our electron deficient carbon. Remember, all of these are going to go through our electron deficient carbon. That is our site of our nucleophilic substitution. At the same time as this happens, our carbon bromine bond is going to break and we're going to have heterolytic fission, meaning that the electrons are going to go with one of the atoms, not with two of them. If the electrons are split between two, that's homolytic fission and we get free radicals. This time we're getting heterolytic fission because we're forming ions. And this is going to form an alcohol and a bromide ion as our products. So let's have a quick look at a mechanism for this. So we have our hydroxide that contains two electrons and a lone pair. They are going to attack using a curly arrow, of course, to show the movement of the electrons. They're going to attack our electron deficient carbon, and the electrons from the carbon-bromine bond are going to go onto the bromine to form a bromide ion. And we're going to form a new bond between our carbon and our oxygen group here to form our alcohol. So we get alcohol and a bromide ion. Reaction number 3 is the reaction of a halogenoalkane, again by heating under reflux. This time we are heating it with potassium cyanide and ethanol, and we're going to make a nitrile. Now, we do not need to know the mechanism for this reaction. Again, this will be touched on later in year 13 in the organic sections. What we do need to know is that the attacking nucleophile is this CN ion, and an example of what happens is our reaction here. So we have our bromoethane being attacked by the CN, and we're going to form this nitrile group. What you may notice is that this first reagent has 2 carbons, whereas our product has 3 carbons. This is actually a very useful way of lengthening a carbon chain, which is very, very useful in organic synthesis. Organic synthesis is a topic that is again in year 13 and topic 20, and you will come back to this particular reaction as a way to lengthen our chain in order to make a new product. Now we can look at reaction number 4, which is the heating of a halogenoalkane with ammonia solution under pressure in a sealed tube to make a primary amine. Now we do need to do this under pressure in a sealed tube because we are using ammonia gas. And of course, if we don't have it on the sealed tube, the gas will escape. So our attacking nucleophile is our ammonia molecule. Please remember that ammonia contains a lone pair, so it can act as a nucleophile. That lone pair will attack into our molecule. And an example of our reaction is shown here, where we make our primary amine, which is this here, and we also make a hydrogen halide. The biggest difference with this particular reaction is that the hydrogen iodide is an acidic substance, so it's going to react with the basic organic molecule, so our amine, in order to form a salt. Now, we don't want this salt to be formed, so what we actually do is we use a very high excess of ammonia, and it avoids this salt to be formed. This would be the salt that would be formed, but as we said, we want to avoid that. So what we do is we add in this excess of ammonia, and we end up making an ammonium salt plus our primary amine, and we can combine them into this equation down here. Now, as we've said previously, you do need to know the mechanism for this particular reaction. It can come up in an exam. You could be asked to reproduce it, but it is very straightforward in comparison to some of the other mechanisms, and it does follow very similar patterns that we've seen. So we start with our ammonia nucleophile, and it has its lone pair, and the curly arrow will travel from the lone pair on the nitrogen to the electron deficient carbon, and then our electrons between the carbon to chlorine bond are going to travel onto our chloride ion, and we're going to form this chloride, and we're going to form our intermediate here. Now, what happens when we have our excess, because these two things would form our salt, and we do not want that. So we have our excess ammonia being added, and it basically, we get this lone pair again, this time attacking the hydrogen, and our electrons from the nitrogen-hydrogen bond here go on to the nitrogen, of course giving the nitrogen back its lone pair and forming an ammonium. And this ammonium will join up with this chlorine and we will form ammonium chloride salt. Now the last reaction that we need to know about before we look at some past papers is an elimination reaction. So if we have reaction number 2 being carried out in ethanolic reactions, now just a reminder, that was the addition of the potassium hydroxide and aqueous was reaction number 2. If we have this happening in ethanolic conditions, so being dissolved into ethanol, we get a different reaction happening. Under these reactions, our OH actually acts as a base instead of a nucleophile. And what happens is it causes our hydrogen atom next to our electron deficient carbon to be removed as water. So we're actually eliminating an atom in this particular reaction. And what we do is we get water being formed and we form an alkene. So this is a way that on our organic reactions map, this is a way for us to go from a halogenoalkane back to an alkene. You can see here that we lose, so the potassium bonds in with the bromine, and then this hydrogen bonds with the OH, and we get water and potassium bromide, and we form our double bond here because we've lost an atom from each of these two carbons. So let's have a look at a past paper question for this, or a number of different questions. I've looked at some multiple choice as well as a full length questions. So the paper that I've taken these from is the January 2018 paper. So the first one is looking at the properties of our liquid chloro-2-butane. So let's just draw it out real quick. So the butane is going to give us 4 carbons. It's the second carbon that the chloro's on, and then we draw hydrogens for all the rest. So in terms of solubility in water, well, we know that with it being a chlorobutane and with it being mostly an organic molecule, we're going to have an insoluble substance in water. So we can automatically discount C and D. Now we just need to look at what effect does it have on a charged rod. What effect would a charged rod have on the stream of liquid? Now, because we have this carbon to chlorine bond here, which is very polar, it does give a slight polarity in the molecule, so that's going to have an effect on our charged rod, and actually it's going to cause our stream to be diverted. So the answer to this question is A. For question 13, we're looking at the organic elimination products from 2-bromobutane. So this is very much the last topic that we were just looking at there. So let's just draw it out again. So we have 2-bromobutane. Now we will obviously remove this bromine, but the question that we can't work out, or the question that we have, is that what side does the hydrogen come from? It can either come from this side or it can come from this side. Now we can't actually control this. We do get a major and a minor product depending on the carbocations, but we don't need to go into enough detail about that. What we do need to be aware of is that we can make at least 2 different products here. So we can end up having the double bond between carbons 1 and 2, or we can have the double bond between carbons 2 and 3. Now that you may then think the answer is going to be 2, however, we do need to consider that butene can have EZ isomers. You can get E-butene and Z-butene. So now we have 1 isomer from our butanene and our 2 geometric isomers. So the answer to this is actually 3. don't get caught out by saying 2, thinking that we can only get one geometric isomer. We do need to remember that we can have more than one. Okay, let's look at a full-length question on this. So we're going to have a question about the preparation and the properties of iodobutane. So iodobutane can be prepared by warming a mixture of damp red phosphorus with iodine to produce phosphorus iodide, and this reacts with butan-1-ol to form the iodobutane. We want to complete the balanced equation for the formation of the 1-iodobutane. We do not need state symbols. Now this may look at first glance quite confusing, but actually all the information that we need is all in the question. So we know that we're going to form C4H9I. We have our other product. Well, the other product is going to be the phosphorus reacting with the oxygens and the waters that are being removed from the alcohol here. Now we do need to take into account that we have got this difference in our number of iodines. So if we have Pi3, our phosphorus 3 iodide, we're going to be having to use all 3 of our iodines in our iodobutane. That then gives us also having to balance out that we need to start with 3. So our reaction reads as 3 butan-1-ols plus phosphorus 3 iodide gives us 3 1-iodobutanes plus H3PO3. Now the 1-iodobutane, as we said, has been formed, but we can actually draw 4 different structural isomers of this. Now we're in the previous one talking about the iodobutane, but we can also, of course, have it as different structural isomers. So the first one is going to be very simply. So we've got carbons 1, 2, 3, 4 connected to an iodine. Okay. We can then also have a branch. Again, another branch. And we can form our basic 2-iodobutane. So remember, whenever we're drawing any structural isomers, the first thing that you should do is look at the position of the iodine atom and then look at the chain length. And all you do is you either move the position of the iodine or you keep the iodine where it is and you reduce the chain length until you get all 4 isomers. If you got 2 or 3 correct, you would get 1 mark. If you get all 4 correct, you would get 2 marks. Now you can do them in displayed or structural formula. I've chosen to do that in skeletal formula because of course that's what the question asks for. If you do use displayed or structural formula, you do however still get 1 mark. So let's move on to another question where we're looking at the iodobutane being dissolved in ethanol with the hot aqueous silver nitrate to form a yellow precipitate. Okay, this reaction is going to involve 2 steps. Well, this is going back to our reaction number 2, which is the reaction with our hydroxide. This is our going back to reaction number 1, which is our reaction with our hydrolysis. Okay, so our attacking reagent in this case is going to be water, and we're looking at the lone pair that is on the water. And the type of mechanism, well, it's going to be a nucleophile that is attacking, so we're going to have a nucleophilic reaction, and they always, for halogenoalkanes, are going to be substitution reactions. Then we have to look at the ionic equation for the formation of the yellow precipitate, and of course it's going to ask us to include state symbols here. Be very, very careful that you always include the state symbols when they are asked for. This is only for 1 mark. If you don't include the state symbols, you are going to throw that away. So the ionic equation is going to be our silver, which is aqueous, reacting with our iodide, which is also aqueous, to form our silver iodide precipitate, which of course is going to be solid. Now we're going to look at our final question, which is looking at the reaction between the iodobutane and excess ammonia. So that is going back to reaction number 4, which is the excess ammonia, and we're going to form 2 products. Okay, it says, and we can identify them by name or by formula. Well, if we have butane as our alkyl group, we are going to have a butyl amine being formed, and that is simply the name that we use, is butyl amine. We can also write 1-amino butane. Either answer would be accepted. Now that is just one of our products. Of course, with the excess ammonia, we know that we're also going to make some form of salt, and the salt is always going to be an ammonium. So we just have to double check what is our halogen, and we're going to form ammonium iodide. My one piece of advice for this particular question would be this part here, the name and the formula. The name or the formula. You can write both. That is absolutely acceptable. However, if one of them is wrong, you lose that mark. So if you're not sure on the formulas, or you're not 100% sure on the name, do not write them. Write one or the other. Pick the one that you are most confident with. Now you can, of course, check all of your answers in the mark schemes that you can find at the end of the presentation. And you can go back and check through each of the questions that you have answered. That is everything for the halogenoalkanes. I hope that you have found this video useful and that you've been able to understand all of the reactions that we need. Check back later for some additional videos on the organic section, and I hope to see you coming back soon.